Good morning. I'm Mrs. Gilbert, and I'm here to guide you through Algebra II. In case you missed last week, we were working on exponentials and logarithmic functions. And so our first essential concept that we're talking about is being able to graph these functions. So last week we talked specifically about exponentials. And so we're going to talk about what a logarithm is and getting to graphing logarithms. Just in case you want, I have a Prezi with the notes on here, just in case you want to look at it separately. So let's review exponential functions first. So we're talking about our form, which is y equals a times b raised to the x power. And so we're going to talk about each of these components. So b is the part that's being multiplied. And as we multiply, our growth happens. So b can't be 1 or 0 because neither of these would create growth. And b can't be negative or less than 0 because we want to keep our answers real as opposed to imaginary. So last week we also talked about the difference between decay and growth. And decay was when b was between 0 and 1, and growth happened when b was greater than 1. And then if we talk about A is for any parent graph, our initial value. And so if it's positive, it's going to be above the asymptote, and if it's negative, it's going to be below. Right? So I want you to be thinking about these. As we look at these equations, we're looking at what power is giving us an answer. So for the first one, we're looking at what power of 2 would give us 128. So if you're thinking about it, hopefully you're remembering that we're trying to multiply, how many times do we multiply 2 together to get 128? And that would be 7. So when we're looking at the next one, what power of 5 would get us to 125? 1 over 125. So this is kind of a two-step part, right? So we're looking at the fraction. Do you remember your rules for exponents? What would make us create a fraction from a whole number? Hopefully you remember that it's a negative, right? I like to tell my kids that if they have a negative exponent, it wants to go across the street. So it's going from above our fraction bar to below it. And if we're looking at the 5 to the 125, we're looking at 5 times 5 is 25, times 5 is 125. So we know that that would be a power of 3. So our answer would be, our exponent would be a negative 3. And the same idea for the next one, except for this time we have 1/4 going to a 16. So we're looking at a fraction going to a whole number, and it's still the same kind of concept with our negative because it's in the denominator, the 4 is in the denominator, and we want it to be above in the numerator. So to do that, we would have to use a negative exponent, and then we would go from 4 to 16, which hopefully you know is 2. So our answer would be a negative 2. So I want you to look at the next one and try this one on your own for a second. And so hopefully you got that 3 times 3 was 9, and 9 times 3 was 27. So our exponent, our value for D, would be 3. So the next two are hopefully pretty easy if you remember. So anything with an what exponent would give you itself, right? So 7 to the power of 1 is going to give you 7. So we know that F is 7. And we know that when we look at what exponent would always give you 1. So it doesn't even matter if that was a 6 or a 256. Anything raised to the 0 power is 1. So we know that that's going to be a 0. So we're looking at this relationship of trying to find a power when we know the base and our answer. So I want you to look at 3, 81, and 4. So I'm going to rearrange these numbers to kind of help illustrate what I want you to see. So I'm going to kind of rearrange them so that we can see the relationship. So we know that when 3 raised to the 4th power is 81. So we would use an exponent to show that. 3 to the 4th power. And when we're looking at 81 and 4, we know that the 4th root of 81 is 3. So we would use a radical sign or a fractional exponent to show that relationship. So how do we show the relationship when we want to know the power? And this is where logarithms come in. We use logarithms as an operation to show that we're looking at the power between the base and what our answer would be in an exponential. And we use a logarithm. So logarithm, we use log, and it's an operation. They're not variables, all right? It's just telling us that we are looking for the power of what power of 3 would give us 81. So you can see that the 3 is little and kind of below, and that's where our base is going, the 3, and we're looking for 81, which would be 4. All right, so let's talk more about these logarithms. Okay, so the parts of a logarithm. So we know it's related to the exponential, right? So we would write log, and then we would have our base. It's the same base in our exponential, okay? So this is the same number. We're just going to write it small in subscript, right? And then the argument is the next part of our logarithm, which is the answer to our exponential. So they are the same number. Okay? And then we're going to talk about the exponent. The exponent is the little superscript on our exponential, and it becomes our answer for the logarithm. All right, I want to show you a quick thing I found. You can just kind of see that we're going back and forth. The relationships, it's just a different way to show the relationship. Okay. So I thought that would be kind of funny. So we're converting forms. So we're showing, I have the picture of Bumblebee, because he's got 2 different forms. And he's the same character, whether he's in his transformer or his car form, but they have specific uses in each form. Okay, so we're going to convert from our logarithmic form to our exponential form. So our base is 4, so that is our base in our exponential, and then you're going to kind of come around to the end, which our answer is 1/2, and that's going to become our exponent, and then the 2 becomes our answer when we're in exponential form. Okay? So right now, we're not solving these. We are just rearranging them. So you don't have to worry about whether this is true or not. But we do know that 4 raised to the 1/2, which is the same as the square root of 4, would be 2. Right? So let's try another one. I want you to think about this one. How would you set this one up as an exponential? All right, hopefully you took the 8, which is our base, it's the little number, and it becomes our big number. The exponent is a 2, and our answer is 64. All right, so let's go the other direction. Let's take an exponential, and let's turn it into a logarithm. All right, so 2 is our base, so it's going to become the small number. 1/2, our answer, it becomes our argument in the logarithm. And then the exponent is a -1, which is our answer in our logarithmic form. Okay, so try this one. And hopefully you got 1/7 is the base. So it's okay to have a fraction in your base. The argument is 49, which is the answer in our exponential, and the answer in our logarithm is the exponent for the other one. Hopefully, I'm going to give you a couple of seconds to look at that, just because when I'm saying it, it sounds a little confusing. All right, so a little math joke. We're keeping it real because we don't want imaginary answers. So from our rules from the exponential, we knew that b couldn't be 1 or 0, and that b has to be bigger than 0, or it can't be negative. Okay? So these same rules still apply in our logarithms because they're related. But we have a couple of new rules because of the setup. Since b isn't 0, our argument can't be 0. And it can't be, since b is negative, can't be negative, our argument cannot be negative either. So if you see that that argument, the big number in the logarithm, is 0 or negative, those are going to be undefined. All right? So I want you to keep in mind that this is an operation, and when the base and the argument are filled out, you're going to get a number. And so this is a table of logarithms, kind of like a multiplication chart, how people used to find logarithms. And basically all of these numbers are in your calculator now, kind of like your multiplication chart is in your calculator as well. So I just wanted you guys to realize that like 5 plus 8 is going to give us a number, right? So logarithms are going to do the same sort of thing. So log base 5, 25 is going to give us the number 2. All right, so I want you to, we're going to evaluate some of these. All right, so we're looking at log base 10 of 100, right? So we're looking for what exponent of 10 gives us 100, so that's 2. Okay. What exponent of 2 gives us 16? 4. I used 7s a lot, didn't I? What exponent of 7 would give us 7? 1. And what exponent of 0 would give us, I just gave it away. What exponent of 8, which would be 0, would give us 1? And this next one, what exponent of 0 would give us 5? Hopefully you realize that's not going to happen, so we can't be 0. The base can't be 0. It would be undefined, right? This next one's a little tricky, right? What power of 36 would give us 6? Hopefully you got, well, we know that 6 is the square root of 36, which would give us a power of 1/2. If you remember, you're switching from radicals to exponential form. So I want you to guys kind of know that the answers to a logarithm can be negative and can be fractions. Okay, but our argument and our base cannot be negative. Okay. And just in case you're wondering, you're like, I have this log button on my calculator, but it doesn't ever have a base. That's because the base is automatically assumed to be 10. All right? So if you press the log button and 100, some of your calculators might be backwards. You might have to put the 100 in first and then log. I don't understand who made the rules for calculators, but you should get 2 because it's the same as having a base 10. Okay? So getting back to our concept that we're looking for, we're looking at graphing. So I wanted to review quickly the graphing for exponentials. So we talked about growth, which is our green line here, is going away from our asymptote, which is the blue dotted line. So if you remember, the asymptote is what our graph is heading towards in either as it goes left or right. In our cases, they're always, for exponentials, they're going to go left and right. So our asymptote is going to be headed as we go left towards our asymptote, and as we go right away from it. So that's going to be growth, right? And decay means we're coming towards our asymptote as we go right, which is our red. So, and don't forget our initial value, which is affected by our A and any shifting we do. Okay. So let's look at this next slide. So these two, I know I changed the color, so I'm sorry. The growth is now red and the decay is blue. But we're going to plot these points. all right? So we're going to take this first one. If we plug in -1 into our logarithm, what kind of answer would we get? Well, hopefully you remembered that it's undefined. So we can't really plot this point, right? Can we plot 0? No, because x is 0, sorry. If we're plugging in 0 for our logarithm, it's going to be undefined. Oh, I forgot to mention our base is going to be 2 here. All right, so if we plug in 1/4, we're going from a 2 to the 1/4. What power of 2 would give us 1/4? So hopefully you're thinking 2 to 4 is 2, but that 1/4 might be a little tricky. Hopefully you're remembering it should be a negative, so it's going to be a -2. The same idea for the next one, right? -1. Right? So we're plotting these. So I know you can, it's kind of hard to see, but so between the 1, I went 1/4 of the way over, and then we went down to -2. And then halfway through, we went down to -1 when we're plotting. All right? So when we plug in 1, we're going to get any argument where you get a 1, your answer is always going to be 0. Okay? So when we plug in 2, we're going to get 1. So what power of 2 would give us 4? So log base 2, 4 is the same as 2. What power of 2 gives us 4, which is 2? And log base 2, 8 was still the same thing as asking us what power of 2 would give us 8, which is 3. All right, so I'm going to switch up the graphs a little bit so that we can kind of see what's going on. All right, so as we're looking at this, we can see that we have an asymptote for our logarithm as well. But instead of going left and right, our asymptote is going up and down. Okay, so this idea of it going up and down, it's never going to be, our answer is never going to be negative, which makes sense. We're never going to have a negative x, which makes sense, sorry. Ooh, okay. And as you look at this, hopefully you can see that the red one was 2 raised to the x power. And so we're keeping the base with the 2 and with our exponent being x versus a log with a base 2 with the argument being x. And these are actually inverse functions, which you can see by looking at x equals y equals x, and they're going to be inverses, which means they're reflected over y equals x. All right, so I wanted to look at some other graphs real quick, and we can show some of the things that happen as we look at them. Okay, so on the far left, I have basically the graph we just did. So we have 2 to the x power and log base 2x. And so the middle one, I kept our log base 2x, and then we have a negative in front, which flips it over our x-axis. And the same idea would happen with our exponential. So just kind of keep in mind when you're looking at your graphs, especially sometimes when you're doing the matching or if you're looking at what kind of relationship is happening, that it looks like our asymptote is going up and down. It's going to be a logarithm. If our asymptote is horizontal, it's going to be an exponential. And so if it's going from our asymptote and going down, we're going to probably have a negative in the front. All right? All right. So our next one is our transformations. Again, this time we're reflecting over the y-axis. So we're looking at the negative in front of the x. So when we do this, I know you're like, hey, we said we can't have negatives, but we can because our argument isn't x, it's negative x. So whenever we plug in a negative into negative x, we're going to get a positive. That means no positive x is ever going to give us an answer for our exponentials. Okay? So, and we're looking at our y to the, with the base of 2 going to a negative exponent. And you're like, hopefully this looks like decay. How is this different? So if you remember what we were talking about with our negative exponents, always creating the reciprocal, right? So we want to move that 2 from the numerator to the denominator. It does create 1/2, which would make our graph a decay graph. All right. I did want to show you a couple of others. All right. So hopefully you talked a little bit about shifting your graphs. And these are the ones that would move our asymptote. This is the main reason why I wanted to bring this one up. All right. So if we are adding in our x value, it's going to shift left, and if we subtracted, it would shift right. So our asymptote doesn't move when we have our exponential graph, but our asymptote moves when we have our logarithmic graph because we're shifting left and right. In our exponential, our asymptote doesn't shift when we move left and right side. But it does move when we go up and down, which is basically kind of adding an extra constant out in the end. So here I moved it down instead of up just so it would be a little bit more visible. So we're literally taking this graph and we are subtracting 3, so our whole asymptote is moving. As opposed to our logarithms, when we do that, our asymptote still stays where it is. And a quick overview, and you're like, all my graphs have been with a base 2. So I wanted to show you a quick couple ones that are not base 2 anymore. So you can kind of see that they're still all going through this initial point because I didn't add any aids. So they're all going through this point, and they're all how fast they're growing as the exponential. So it's going to go faster. It's going to be steeper with the blue, and then the orangish yellow is going to be doesn't take as much because it's closer to 1. All right. Well, it was good to be with you today, and I'm hoping that this will help and that I will see you next week.